So last time we saw this, we saw an example of a mixed strategy, which was to play a third, a third, a third in our rock, paper, scissors game. All right, and today we're going to be formal, we're going to define mixed strategies, and we're going to talk about them, and it's going to take a while. All right, so let's start with a formal definition. A mixed strategy, and I'll develop notation as I'm going along, so let me call it P sub I being the person who's playing it. P sub I is a randomization. It's a randomization over I's pure strategies. All right, so in particular, we're going to use the notation P sub I of Si to be the probability that player I plays Si, given that he's mixing using Pi. All right, so Pi Si is the probability that Pi assigns to the pure strategy Si. And to immediately refer that back to our example, so for example, if I'm playing third, a third, a third in rock, paper, scissors, then Pi is a third, a third, a third, and Pi of rock, that would Pi of R, is a third. All right, so without belaboring it, that's all I'm doing here, is developing some notation. All right, let's immediately encounter two things you might have questions about. So the first is that in principle, Pi Si could be 0. All right, so just because I'm playing a mixed strategy, it doesn't mean I have to involve all of my strategies. All right, I could be playing a mixed strategy on 2 of my strategies and leave the other one with 0 probability. So for example, again in rock, paper, scissors, we could think of the strategy a half, 0. Right, in this strategy, I assign, I play rock half the time, I play paper half the time, but I never play scissors. All right, so everyone understand that? And while we're here, let's look at the other extreme. The probability assigned by my mixed strategy to a particular Si could be 1. Right, it could be that I assign all the probability to a particular strategy. What would we call a mixed strategy that assigns probability 1 to one of the pure strategies? What's a good name for that? That's a pure strategy, right? That's a pure strategy. All right? So notice that we can think of pure strategies as the special case of a mixed strategy that assigns all the weight to a particular pure strategy. So for example, if Pi rock was 1, that's equivalent to saying that I'm playing the pure strategy rock. All right, i.e. a pure strategy. All right, so there's nothing here. I'm just being a little bit nerdy about developing notation and making sure that everything is in place. All right, and just to point out again, one consequence of this is we've now got our pure strategies embedded in our mixed strategies. Right, when I talk about a mixed strategy, I really am including in those all of the pure strategies. All right. So let's proceed. Maybe I push that up a little high, sorry. All right. So now I want to think about what are the payoffs that I get from mixed strategies. And again, I'm going to go a little slowly because it's a little tricky at first, and we'll get used to this. Don't panic. We'll get used to this as we go on and as you see them in homework assignments and in class. All right, so let's talk about the payoffs from a mixed strategy. Payoffs from mixed strategies. All right, and in particular, what we're going to worry about are expected payoffs. So the expected payoff of the mixed strategy P let's be consistent and call it PI, the mixed strategy PI, is what? It's the weighted average. It's a weighted average, or a weighted mixture, if you like, of the expected payoffs of each of the pure strategies in the mix. All right, so this is a long way of saying something, and again, I think is a little bit obvious, but let me just say it again. The way in which we figure out the expected payoff of a mixed strategy is we take the appropriately weighted average of the expected payoffs I would get from the pure strategies over which I'm mixing. All right, to make that less abstract, let's immediately look at an example. So here's an example we'll come back to several times, but just once today. And this is a game that you've seen before. Here is the game Battle of the Sexes, in which player A can choose player 1 can choose capital A and B, and player 2 can choose little a and b. All right? And what I want to do is I want to figure out the payoff from particular strategies. So suppose that P is what's being played by player 1, and P is, let's say, 1/5, 4/5. So what do I mean by that? I mean that player 1 is assigning a fifth to playing A and 4/5 to playing B. All right? And suppose that Q, so I'm going to use P and Q because it's convenient to do so rather than calling them P1 and P2. So suppose that Q is the mixture that player 2 is choosing, and she's choosing a half-half. So she's putting probability a half on little a and probability a half on little b. And just to notice that I switched notation on you a little bit, and for this example, to keep life easy, I'm going to use P to be rows mixtures and Q to be columns mixtures. Right? And the question I want to answer is, what is the expected payoff in this case of P? What is P's expected payoff? All right? And the way I'm going to do that is I'm first of all going to ask, what is the expected payoff of each of the pure strategies that P involves, over which P is, the pure strategies involved in P. Right? So to start off, right, so the first step is ask, what is the expected payoff for player 1 of playing A against Q? And what is the expected payoff for player 1 of playing B against Q? That'll be our first question, and we'll come back and construct the payoff for P. All right, so these are things we can do, I think. So the expected payoff of A against Q is what? Well, half the time if you play A, you're going to find your opponent is playing little a, in which case you'll get 2. And half the time when you play A, you'll find your opponent is playing B, in which case you'll get 0. All right, so let's just write that up. So I'm going to get 2 with probability a half plus 0 with probability a half. All right, everyone happy with that? And that gives me 1. Okay, please correct my math on this. It's very easy at the board to make mistakes, but I think that one is right. Okay? Conversely, what if I played B? What's the expected payoff for the row player of playing B against Q, where Q is a half-half? So half the time when I play B, I'll meet a player 2 playing little a, and I'll get 0. And half the time I'll find player 2 is playing little b, and I'll get 1. All right, so let's write that up. So I'll get 0 half the time, and I'll get 1 half the time for an average of a half. All right? Okay, that's the first thing I ask, and now to finish the job, I now want to figure out what is the expected payoff for player 1 of using P against Q. That was the question I really wanted to start off with. All right, what's the way to think about this? Well, P is 1/5 of the time. According to P, 1/5 of the time, player 1 is playing A, and 4/5 of the time, player 1 is playing B. Is that right? So to work out the expected payoff, what we're going to do is we're going to take 1/5 of the time, in which case he's playing A, and he'll get the expected payoff he would have got from playing A against Q, and 4/5 of the time he's going to be playing B, in which case he'll get the expected payoff from playing B against Q. All right, and now just plugging in some numbers to that from above, so we've got 1/5 of the time he's doing the expected payoff from A against Q, and that's this number we worked out already. All right, so this number here can come down here, 1. And 4/5 of the time he's playing B against Q, in which case his expected payoff was 1/2. So this 1/2 comes in here. All right. Everyone okay so far? How I constructed it so far? Is this podium in the way of you guys? Are you okay? Let me push it slightly. You okay? All right. And so the total here is what? It's going to be 1/5 of 1 plus 4/5 of 1/2. 4/5 of 1/2 is 2/5, so I've got a total of 3/5. All right, so the total here is 3/5. All right, everyone understand how I did that? Okay. Now, while it's here, let's notice something. When I played P, some of the time I played A, and some of the time I played B. All right? And when I ended up playing A, I got A's expected payoff, and when I played B, I got B's expected payoff. So the number I ended up with, 3/5, must lie between the payoff I would have got from A, which is 1, and the payoff I would have got from B, which is 1/2. Is that right? Is that right? So 3/5 lies between 1/2 and 1. Everyone okay with that? Yeah? Yeah? Now that's a simple but very general and very useful idea, it turns out. Right? The idea here is that the payoff I'm going to get must lie between the expected payoffs I would have got from the pure strategies. Let me say it again. In general, when I play a mixed strategy, the expected payoff I get is a weighted average of the expected payoffs of each of the pure strategies in the mix. And weighted averages always lie inside the payoffs that are involved in the mix. All right? All right. So let me try and push that simple idea a little harder. Suppose I was going to take the average height in the class, the average height in this class. All right? So let me just, rather than use the class, let me just use some TAs here. So let me get these 3 TAs to stand up a second. All right? And suppose I want to figure out the average height of these 3 TAs. All right? So stand up closer together so I can see what's going on here. So I think from where I'm standing, I've got that Ale is the tallest and Murta is the smallest. Is that right? So I don't know instantaneously what this average would be, but I claim that any weighted average of their 3 heights is going to give me a number that's somewhere between the smallest height of the 3, which is Murta's height, and the tallest height of the 3, which is Ale's height. Is that right? Is that correct? All right, so that's a pretty general idea. But thanks, guys. I'll come back to you in a second. All right? All right? And let's think about this somewhere else. Let's think about the batting average of a team. All right? Let's think about the team batting average in baseball. All right? Let's use the Yankees, for example. We know that the team batting average, the average batting average of the Yankees I don't know what it is instantly, I didn't look it up this morning, but I know it lies somewhere between the player who has the highest batting average, which I'm guessing is Jeter, and the lowest, and the person on the team who has the lowest batting average, who's probably one of the pitchers who batted a few times in one of those interleague games. All right? It would have been better if I'd used the Mets, but I feel I should take pity on Mets fans this week and not mention them. All right? All right? So this is a very simple idea. It's deceptively simple. It says averages, weighted averages, lie between the highest thing over which you're averaging and the lowest thing over which you're averaging. All right, everyone okay with that idea? All right? Now this very simple idea is going to have an enormous consequence. And here's the enormous consequence. All right? Simple idea, big consequence. So there's going to be a lesson that follows from this incredibly simple idea. And this is the lesson. If a mixed strategy is a best response, right? So if a mixed strategy is the best thing you can be doing, then each of the pure strategies in the mix, I'm being a little bit loose here, but I mean assigned positive probability in the mix for those people who are nerdy enough to worry about it. Each of the pure strategies in the mix must themselves be best responses. So in particular, each must yield the same expected payoff. All right, so here's a big conclusion that follows from that incredibly simple idea about averages lying between the highest one and the lowest one. And let's draw ourselves from that lesson to this big conclusion. Right? What is the conclusion? The conclusion is if a mixed strategy is a best response, if it's the best thing I can do is to play a mixed strategy, then each of the pure strategies which I'm playing in that mix, which I'm assigning positive probability to in that mix, must themselves be best responses. All right? In particular, each of them therefore must yield the same expected payoff. So let's go back to our example. Sorry guys, can I steal my 3 TAs again? And suppose the thing I'm involved in, I should have made this easier before, let me come down a little bit. I'll stand above here. This is good, okay? So suppose the game I'm involved in, the payoff in the game is a game in which I have to choose the tallest group of my TAs. Right? So my payoff is going to be the average height of whichever subgroup of my TAs I pick. All right? And these are my 3 choices. All right? So if I pick more than one of them, right, I'm going to get a weighted average. That's a mixed strategy. All right? My aim here is to maximize the height of whatever subgroup I pick. All right? So in this game, here's my 3 choices. Here's my 3 pure strategies. My 3 pure strategies are to pick Murto, Ale, or Jake. All right, those are my 3 pure strategies. And my mixture, I could mix these 2, I could mix these 2, I could mix all 3. All right? But remember, my payoff here is to get the group, the average, as high as I can. So how am I going to get the average as high as I can? How am I going to get the average as high as I can? This is cheating here. I get the average as high as I can. I'm going to kick out Murto for a start, all right? Sorry, so, all right, because Murto's just bringing down the average. Is that right? All right, average height, I should say. All right, there's nothing. All right, right, and actually, all right, and I think I'm going to kick out Jake as well. I think. Can people help from the front? I think I'm probably going to kick out Jake as well because that way I just have Ale. Right? So if it was the case I was picking both of them, it would have to be they were equally tall, right? But since they're not equally tall, I should just pick the best one. Right? Let's go back to my Yankees example. If I want to pick a sub-team of the Yankees, I'm allowed to pick any number of people to have the highest average batting average in that sub-team. The way to do it is to find the Yankee who has the highest batting average and just pick him. All right? Let's do one more example. Let me use the front row of students here. All right? So here's my, can I get this front row of students to stand up a second? All right, so this part of the row. All right? And suppose my aim in life is to construct the highest average GPA. I'm not going to embarrass these guys and ask them what their GPAs are. All right? So my aim in life here is to pick some subgroup of these 1, 2, 3, 4, 5, 6, 7, 8 students, such that the average GPA of that subgroup is as high as I can make it. All right? So what will I do here? So this being Yale, I'll just find the people who have the 4.0 GPAs and just pick them. Is that right? All right, you might think, well, why not include somebody who has a 3.9 GPA? That's pretty good. So why not? Because if there's anybody in this group who has a 4.0 GPA, I'd do better just to pick that person. The 3.9 person would just be pulling down the average. Now suppose there's nobody with a 4.0 GPA, and suppose it's the case that three of these people, let's say these 3 people, have a 3.9 GPA. Right? So these 3 have 3.9 GPA, imagine that, and these other people, they've got horrible grades like B+ somewhere, all right? All right? So these are our future law school students, and these are the people who knows what they're going to end up doing, being president probably, all right? Right? All right? Right? So to construct the group with the highest average GPA, what am I going to do? Well, first I'll throw out all these guys with low GPA so they can all sit down. Right? And I'll look at these last 3, and these last 3, if they're all in the group, they better all have the same GPA. Right? Why not? If I'm trying to maximize the average of my group, if any of them had a lower GPA, I should kick them out. And if one of them has a higher GPA than the other 2, I should kick out both the other 2. So if I'm including all 3 of them in my constructing of the average, all of them must have the same GPA, which I'm going to assume is 3.9 to assume you can still make it into law school. All right, everyone understand that? Yep? Yep? Okay, thanks guys. All right? All right, so that's the way I want to think about this, all right? So the idea here is, if I'm using a mixed strategy as a best response, right, it must be the case that everything on which I'm mixing is itself best. And the reason is, if it wasn't, kick out the thing that isn't best, and my average will go up. All right, all right. So that leads us to the next idea, but before I do, just for formality, let me add a definition. The definition is this. A mixed strategy profile. What I'm going to do now is I'm going to define Nash equilibrium again, just so we have it on a note somewhere. So a mixed strategy profile, should be a hyphen there, P1 star, P2 star, all the way up to Pn star, is a mixed strategy Nash equilibrium if for each player I, so for each I, bring it over here, for each player I, that player's mixed strategy, Pi star, is a best response for player I to the strategies everyone else is picking, P minus I star. So I'm exploiting our, by now, well-developed notation for player strategies. Let me get some more chalk. All right? So this definition of Nash equilibrium, it's exactly the same as the definition of Nash equilibrium we've been using now for several weeks, except everywhere where before we saw a pure strategy, which was an S, I've replaced it with a P. Right? It's the same definition, except I'm using mixed strategies instead of pure strategies. But an implication of our lesson is what? It's that if Pi star is part of a Nash equilibrium, so if Pi star is a best response to whatever else is doing, P minus I star, then each of the pure strategies involved in Pi star must itself be a best response. All right, so an implication of the lesson is the lesson implies the following. If Pi star of a particular strategy is positive, so in other words, I'm using this strategy in my mix, then that strategy is also a best response to what everyone else is doing. All right? Okay. So from a math point of view, this is the big idea of the day, this board. Okay, and just if you're having trouble reading this at the back, trust me, I've written that up on the handout that will appear magically on the computer at the end of class. Right? And at the moment you're staring at this, and it's all a bit new, and as well as being new, you're saying, okay, but so what? Why do I care about this seemingly mundane fact? All right? And the reason we're going to turn out to care about this seemingly mundane fact is that this fact is going to make it remarkably easy to find Nash equilibria. All right? This fact, right, this lesson, this idea that if I'm playing a pure strategy as part of the mix, it must itself be a best response. That's going to be the trick we're going to use in finding mixed strategy Nash equilibria. All right. Now the only way I can illustrate that to you is to do it. So I'm going to spend the rest of today just doing that. I'm going to look at a game, and we're going to go through this game. We'll discuss it a little bit because it's a fun game, and we're going to find the mixed strategy equilibria of this game. Okay, everyone know where we're going? I want to make sure before I go on, are people looking very sort of deer in the headlamps? That was a lot of formality to get through in a short period of time. So how anyone want to ask a question at this point? Are you okay? Okay to go on? All right. So just remember that the conclusion here comes from this very simple idea. The simple idea is the payoff to a weighted average must lie between the best and worst thing involved in the average, and therefore, if I'm including things in there as part of a best response, they must all be good. Right? That's the simple idea. This is the dramatic conclusion. All right. So the only way to prove this to you, and the only way to prove to you that this is useful, is to go ahead and do it. So what I'm going to do is I'm going to clean these boards, and I'm going to start showing an example. All right, and again, don't panic. I think a lot of people at this part of the class have a tendency to panic because it's a new idea and there seems like a lot of math around. None of it's very hard math. It's all kind of arithmetic. It's just this idea of not panicking. All right. So the example I want to look at is going to be from tennis. And I'm going to consider a game within a game played by two tennis players, and let's call them Venus and Serena Williams. All right, so Venus and Serena Williams. So a couple of years ago, we used to use Venus and Serena Williams for this example, and then for a while, I worried that you wouldn't even remember who Venus and Serena Williams were until we picked any two random Russians. But now we're back. Seems like we're back to picking Venus and Serena. All right? So the game within the game is this. Suppose that they're playing and Serena is at the net. Right? Serena is at the net, and the ball is on Venus's court, and Venus has reached the ball, and Venus has to decide whether to try to hit a passing shot past Serena on Serena's left or on Serena's right. And notice I'm going to exclude the possibility of throwing up a lob for now. All right, just to make this manageable. So basically, the choice facing Venus is, should she try to pass Serena to Serena's left, which is Serena's backhand side, or to Serena's right, which is Serena's forehand side? All right, everyone, people are familiar enough with tennis to understand what I'm talking about? Yeah? Yeah? So we're going to assume this is Wimbledon, otherwise no one will be at the net to start with, I guess. This is at Wimbledon. All right, and let's try and put up some payoffs here. All right, so these are going to be the payoffs. I think that this example is originally due to Dixit, but it doesn't. It's not a big deal. I think this example is due to Dixit and Skeeth. All right, so here's some numbers, and I'll explain the numbers in a minute. So this is 50-50, 80-20, 90-10. And 20-80. Okay? So So what are these numbers? So first of all, let me just explain what the strategies are. So I'm assuming the row player is Venus and the column player is Serena. I'm assuming that if Venus chooses L, that means she attempts to pass Serena to Serena's left. All right, we'll orient things from Serena's point of view. And if she hits right, that means she's attempting to pass Serena on Serena's right. All right, and if Serena chooses L, that means she cheats slightly towards her left. Not cheats in the sense of breaking the rules, but cheats in terms of where she's standing or leaning. And if she chooses right, that means she cheats slightly towards her right. So this is cheating towards her backhand, and this is cheating towards her forehand, assuming she's right-handed, which she in fact is. Okay, and what do these numbers mean? So let's start with the easy ones. So if Venus chooses left and Serena chooses right, then Serena has guessed wrong. Is that correct? Right, Serena's guessed wrong, in which case Venus wins the point 80% of the time and Serena wins it 20% of the time. Right? And conversely, if Venus chooses right and Serena chooses left, then again Serena has guessed wrong, and this time Venus wins the point 90% of the time and Serena wins the point 10% of the time. All right, and this should be a familiar idea by now, but why is it the case that these 90s and 80s are not 100%? Why is it the case that if Serena guesses wrong, Venus doesn't win 100% of the time? Anybody? Sometimes we can show hands and we get some mics up. Why isn't it 100% here? Somebody? Yeah, Patrick? Wait for the mic.
Sometimes she hits it out of bounds when she serves.
Right, so yeah, this isn't even a serve, this is a passing shot, but the same is true. So sometimes you're just successfully going to hit it past Serena, but the ball's going to sail out. All right, so that happens 10% of the time here and 20% of the time here. Right, now look at the other two boxes. If Venus hits to Serena's left and Serena guesses left, then we're going to assume that Serena's going to reach the ball and make a volley, but her volley only manages to go in, get over the net and go in, half the time. So the payoffs are 50-50. Half the time Venus wins the point, and half the time Serena wins the point. And conversely, if Venus hits the ball to Serena's right and Serena guesses correctly and chooses right, then we're in this box. Once again, Serena has guessed correctly, and she's going to successfully reach the volley. And this time, she gets it in 80% of the time, so Venus wins the point 20% of the time, and Serena wins it 80% of the time. All right? So just to finish up the description of the game here, notice that we're assuming that Serena is a little better at volleying to her right than she is volleying to her left. Right? So this is her forehand volley, and we're going to assume that that's stronger than her backhand volley. All right? And conversely, we're assuming that Venus's passing shot is a little better when she shoots it to Serena's left than when she shoots it to Serena's right. This is her cross-court passing shot, and this is her down-the-line passing shot. All right? So none of that fine detail matters a great deal, but just if you're interested, that's where the numbers come from. Okay? I'm not claiming this is true data, by the way. I made up these numbers. Actually, I think Dixit made up these numbers. I forget where I got them from. All right? So, okay, everyone understand the game? All right? So now either imagine you are Venus or Serena, or imagine perhaps more realistically that you've become Venus or Serena's coach. Do I have any members of the tennis team here? No? No? Well, imagine you've become their coach, all right? So you take this class, and then you apply to replace their father as being their coach. All right? That's a tough assignment, I would think. All right? So an obvious question is, you are coaching Venus before Wimbledon, you know this situation is going to arise, and you might want to coach Venus on what should she do here. Should she try and pass Serena down the line, or should she try and hit the cross-court volley, cross-court passing shot? All right? And notice that this is a question of, should you, Venus, play to your strength, which is the cross-court passing shot, or should you play to Serena's weakness, all right? Which would be to hit it to Serena's backhand, right? Playing to your strength is to choose right, and playing to Serena's weakness is to choose left. And conversely for Serena, should you lean towards your strength, which I guess is leaning to the right, or should you lean towards Venus's weakness, which I guess is leaning left? All right? And when you look at coaching manuals on this stuff, or you listen to the terrible guys who commentate on tennis for ESPN, oh no, I'm getting in trouble again. Very nice guys who commentate on tennis for ESPN, they say just incredibly dumb things at this point. Right? They say things like, you should always play to your strengths and don't worry about the other person's weakness. Right? I think it won't take much time today to figure out that's not great advice. All right? But people can at least see that this is a difficult problem. Right? It's not an immediately obvious problem. Is that correct? Is that correct? And one reason it's not immediately obvious is not only is no strategy dominated here, but there is no pure strategy Nash equilibrium in this game, right? In this little subgame. There is no pure strategy Nash equilibrium. Notice I've added the qualifier now. Previously I would just have said Nash equilibrium, but now that we have mixed strategies in the picture, I'm going to talk about pure strategy Nash equilibria to be those that are only involving pure strategies. Okay, so why is there no pure strategy Nash equilibrium? Well, let's have a look. So if Serena thought that Venus was going to choose left, then her best response, not surprisingly, is to lean left. And if Serena thought that Venus was going to choose right, then her best response is to cheat to the right. All right, so 50 is bigger than 20 and 80 is bigger than 10. All right, and conversely, if Venus thought that Serena was cheating a bit to the left, then her best response is to hit it to Serena's right. And if Venus thought Serena was leaning to the right, then Venus's best response is to hit it to Serena's left. Okay? So I think that's not at all surprising when you think about it. Not at all surprising you're going to get this little cycle like this. But we can see immediately that these best responses never coincide, so there is no pure strategy equilibrium. Let's just write that up. There's no pure strategy Nash equilibrium. All right. So that leaves us a bit stuck, except I guess you know what the next question is going to be, and I shouldn't leave it in too much suspense. The next question is going to be, okay, there's no pure strategy Nash equilibrium, but we've just introduced a new idea, which was what? It was Nash equilibrium in mixed strategies. Maybe there's going to be a mixed strategy Nash equilibrium. In fact, there is going to be one. All right, so our exercise now is let's find a mixed strategy Nash equilibrium. And before we find it, let's just interpret what it's going to mean. A mixed strategy Nash equilibrium in this game is going to be a mix for Venus between hitting the ball to Serena's left and Serena's right, and a mix for Serena between leaning left and leaning right, such that each person's mix, each person's randomization, is a best response to the other person's randomization. All right? All right? And since these players are sisters and have played each other many, many times, not just in competition but probably in practice, it seems like a reasonable idea that they might have arrived in playing each other at a mixed strategy Nash equilibrium. All right, that's what we want to try and do. Now, how are we going to do that? Okay, so what we're going to do is we're going to exploit the trick that we have here, the lesson here. The lesson we have here says, if players are playing a mixed strategy as part of a Nash equilibrium, each of the pure strategies involved in the mix, each of their pure strategies, must itself be a best response. We're going to use that idea. All right, so let's try and do that. All right, so I'm hoping that by doing this, I'm going to illustrate to you immediately that this idea is actually useful. At least useful if you end up coaching the Williams sisters. All right? So I want to keep this so you can still read it. Let me bring it down a bit. Can people still read it? Okay. So what I want to do is I want to find a mixture for Serena and a mixture for Venus that are equilibrium. All right, and having just put it up there, let me bring it down again. This was not so intelligent of me. I actually want to bring in some notation. So as before, let's assume that, Serena's mix is, let's use Q and 1 minus Q to be Serena's mix, and let's use P and 1 minus P to be Venus's mix. Okay, just establish that notation. So here's the trick. All right, so this is the slightly magic bit of the class. Okay, so pay attention. I'm about to pull a rabbit out of a hat. Trick. To find, what shall I do first? To find Serena's Nash equilibrium mix, so that's Q1 minus Q, what I'm going to do is I'm going to look at Venus's payoffs. So to find Serena's Nash equilibrium mix, the trick is to look at Venus's payoffs. That's going to be my magic trick. All right, let's try and see why. So let's look at Venus's payoffs. Venus's payoffs against Q, right? So Serena is choosing Q1 minus Q. So what are Venus's payoffs? So if she chooses left, then her payoff is 50 with probability Q, and I'm going to use the pointer here and hope that the camera can see this too. She gets 50 with probability Q, and she gets 80 with probability 1 minus Q. Okay? If she chooses right, then she gets 90 with probability Q. All right, 90 with probability Q. And she gets 20 with probability 1 minus Q. Oh, I meant to point to that. 20 with probability 1 minus Q. All right? So what? So what is this? We're looking for a mixed strategy Nash equilibrium. So in particular, not only Serena is mixing, but in this case what we're claiming is Venus is mixing as well. All right? So if Venus is mixing as well, that means that Venus is using the strategy left with some probability, P, and using the strategy right with some probability, 1 minus P. Since Venus sometimes chooses left and sometimes chooses right as her best response to Q, as her best response to Serena, what must be true of the payoff to left and the payoff to right? Let's go through again, right? So we're going to assume that Venus is mixing. So sometimes she chooses left and sometimes she chooses right. And she's in a Nash equilibrium, so she's choosing a best response. So whatever that mix P1 minus P is, it's a best response. Right? Since she's playing a best response of P, and that sometimes involves choosing left and sometimes involves choosing right, it must be the case that what? It must be the case that both left itself and right itself are both themselves best response. Right? Right? If she's mixing between them, it must be that both choosing left or choosing right are themselves best responses. If they weren't, she should just drop them out of the mix. That would raise her average payoff. Right? Just like we dropped out the short TAs to get a high height, and we dropped out the failing Yale students to get a high GPA. Sorry. All right? All right? So if Venus is mixing in this Nash equilibrium, then the payoff to left and to right must be equal. They must both be both left and right must be a best response. So in particular, the expected payoffs must be the same. Is that right? Is that correct? Okay. So what does that allow me to do? It allows me to put an equal sign in here. It allows me to put an equal sign in here. Right? Since left is a best response and right is a best response, so they're both best responses, they must yield the same expected payoff. Here's their expected payoffs, they must be the same. And now I've got one equation and one unknown, and now I'm down to algebra. So let me do the algebra. I claim this expression is equal to that expression. So simplifying a bit, I'm going to get, and you should just watch, make sure I don't get this wrong, I'm going to get 40q. So this implies 40q is equal to 61 minus q. So I took this 50 onto this side and this 20 onto that side. So I have 40q equals 61 minus q, and that implies that q is equal to 0.6. All right, so those last two steps were just algebra. All right. So what was the trick here? The trick was I found q, which is how Serena is mixing, by looking at Venus's payoffs, knowing that Venus is mixing, and hence I can set Venus's payoffs equal to one another. Right, say it again. I found the way in which Serena is mixing by knowing that if Venus is mixing, her expected payoffs must be equal, and I solved out for Serena's mix. This is Serena's mix. Okay? Let's do it again. Let's do it again. And here I'm wishing I had another board. And maybe I don't want to lose those numbers entirely, so I'm going to try and squeeze in a bit. Quite, I know I can do. Let's get rid of this one entirely. There we go. That worked. Let's get rid of this one entirely. I can still see my numbers. And let's do the converse. Let's do the trick again. This time, what I'm going to do is I'm going to figure out how Venus is mixing. I know how Serena's mixing now, so now I'm going to work out how Venus is mixing. Now, to figure out how, it's hidden now, to figure out how Serena was mixing, I used Venus's payoffs. So to find out how Venus is mixing, what am I going to do? I'm going to use Serena's payoffs, all right? So to find Venus's mix, which is P1 minus P, let's be careful, it's her Nash equilibrium mix, use Serena's payoffs. Here we go. So if Serena chooses, so this is S's payoffs, if Serena chooses L, then her payoffs will be what? So, and again, we'll just watch, make sure I don't get this wrong, and I'll point to the things to try and help myself a bit. So with probability P, she'll get 50. All right, so 50 with probability P, and with probability 1 minus p she'll get 10. All right, and if she chooses to lean to the right, to lean towards her forehand, then with probability p, she'll get 20. And with probability 1 minus p, she'll get 80. Okay. And we know that Serena is mixing. We know that Serena is mixing. So since Serena is mixing, what must be true of these two payoffs? What must be true of the two payoffs, the payoff to little l and the payoff to little r? What must be true about them since Serena is using a mixture of these two strategies in Nash equilibrium? It must be the case that both little l is a best response and little r is a best response, in which case the payoff must be, someone shout it out? Equal, thank you, they must be equal. These must be equal. These must be equal. They must be equal since Serena is indifferent between choosing left or right and hence is mixing over them. All right, so again, using the fact that they're equal reduces this to algebra. And again, I'll probably get this wrong, but let me try. So I claim, let's take 20 away from here, I've got 30p equals 70 1 minus p. I hope that's right. That looks right. Again, this is just algebra at this point. So I took 20 away from here and 10 away from there, and this implies that p equals 0.7. All right? So I claim I have now found the mixed strategy Nash equilibrium. Here it is. The Nash equilibrium is as follows. Let's be careful. This is Venus's mix. So Venus is mixing 0.7, 0.3, 0.7 on left and 0.3 on right. And Serena is mixing 0.6, 0.4. All right, so this is Venus's mix, and this is Serena's mix. Venus is shooting to the left of Serena with probability 0.7, and Serena is leaning that way with probability 0.6. All right? So we were able to find this Nash equilibrium by using the trick before. Now let's just reinforce this a little bit by talking about it. So suppose it were the case that Serena, instead of leaning to the left 0.6 of the time, leant to the left more than 0.6 of the time. Right, so suppose you're Venus's coach, and suppose you know that Serena leans to the left more than 0.6 of the time. What would you advise Venus to do? All right, let me try it again. So suppose you're Venus's coach, and suppose you've observed the fact that Serena leans to the left more than 0.6 of the time. What would you advise Venus to do? Yeah, pass to the right. Yeah, shout out, yeah.
Pass to the right.
Pass to the right, exactly. So if Serena cheats to the left more than 0.6 of the time, then Venus's best response is always to shoot to the right. Always to shoot to the right. That maximizes her chance of winning the point. And conversely, if Serena leans to the left less than 0.6 of the time, if Serena leans to the left less than 0.6 of the time, then Venus should do what? Shoot to the left all the time. All right? So if Serena doesn't choose exactly this mix, then Venus's best response is actually a pure strategy. Right, so again, if Serena leans to the left too often, more than 0.6, then Venus should just go right. And if Serena leans to the left too little, then Venus should always go left. Right, and we can do exactly the same the other way around. If Venus shoots to the right, so does her cross-hand passing shot more than 0.7 of the time, and you're Serena's coach, what should you tell Serena to do? Yeah. Go that way all the time. Go that way all the time. All right, so if Venus is hitting it to Serena's left more than 0.7 of the time, Serena should just always go to her left. And if Venus is hitting to the left less than 0.7 of the time, so to the right more than 0.3 of the time, then Serena should always go to the right. Right? All right, so that's how this kind of comes back into the sort of coaching manuals, if you like. Okay, so how am I doing so far? People, have I lost everyone yet, or are people still with me? How many of you play tennis, ever? All right, so all your tennis is going to dramatically improve after today, right? All right. Okay. So now let's make life more interesting. Let's go back to the start. We figured out this is an equilibrium. This is how Venus and Serena play. Venus and Serena know each other perfectly well. They know that they mix this way. They're going to best respond to it. This is going to where they end up. But in the meantime, Serena hires a new coach. And Serena's new coach is just very, very good at teaching Serena how to play at the net, and in particular, how to hit the backhand volley. All right? So Serena's new coach, let's say it's Tony Roche or somebody, is just a brilliant coach, and Tony Roche is able to improve Serena's backhand volley, and that changes these payoffs. So you should rewrite the whole matrix, but I'm going to cheat. All right? So the new game is exactly the same as it was everywhere else, except for now, when Serena gets to the backhand volley, she gets it in 70% of the time. Right? So there used to be 50-50 in that box, and now it's 30-70. All right, so the game has changed because Serena has got better at hitting backhand volleys. And we want to figure out, how is this going to affect play at Wimbledon? All right, how is this going to affect play at Wimbledon? Now, it doesn't take much to check that there is still no pure strategy Nash equilibrium. It's still the case, in fact even more so, that Serena's best response to Venus choosing left is to lean to the left. Right? So it's still the case that the best responses do not coincide. There is still no pure strategy equilibrium. All right? And what we're going to do, of course, is we're going to find a mixed strategy equilibrium. But before we do so, let's think about this intuitively. Let's see if we can intuit an answer. All right? I'm guessing we can't, but let's see if we can intuit an answer. All right? So Serena has improved her backhand volley, and hence when she reaches it, she gets it in more often. All right? So one effect, you might think, is what we might want to call a direct effect. I think there's two effects here. There are two effects. One of these I'm going to call the direct effect. And by effect, I mean in particular an effect on how Serena should play the game. Right? So since Serena has improved her backhand volley, when she reaches that volley, she gets it in more often. So one might say, in that case, you're Serena's coach, in that case, you should lean to the left more often than you did before. Right? Because at least when you get that backhand volley, you're going to get it in more often. So the direct effect says Serena should lean left more. In other words, Q should go up. Is that right? So Serena's now better at playing this backhand volley, so she may as well favor it a bit more, and hence Q will go up. So that's the direct effect, but of course there's a but coming. What's the but? Again, let's see my tennis players here. Raise your hands if you play tennis. Oh, suddenly nobody plays tennis. Come on, raise it, all right, okay. What's the but here? We think Serena's backhand's improved, so she might be tempted to play towards her backhand a bit more often. What's the but? What's the but here? So I claim the but is this. You tell me if I'm wrong. The but is that Venus she's her sister after all, right? So Venus knows that Serena's backhand has improved. So Venus is going to hit it to Serena's left less often than before. Is that right? Right? So since Serena's backhand has improved, Venus is going to hit it to Serena's backhand less often than before, and that might make Serena less inclined to cheat towards her backhand, because the ball's coming that way less often. All right? So this is a indirect or a strategic effect. The strategic effect is Venus hits L less often, so Serena should reduce the number of times that she leans to the left, because the ball's coming that way fewer times. Now notice that these two effects go in opposite directions. Is that right? Right? One of them tends to argue that Q would go up. That's the direct effect. And the other one is more subtle. It says we now have to think about not just how my play has improved, but also how the other person is going to respond to knowing that my play has improved. That's the more subtle effects, and that's going to push Q down. That's going to make it less likely, that's going to argue against leaning to the left. All right, so imagine you're going to be Serena's coach. Which of these effects do you think is going to, let's have a poll. Which of these effects do you think is going to win? The direct effect or the indirect effect? The direct effect or the strategic effect? Who thinks the direct effect? Who would advise Serena to play to her strength a bit more and lean left a bit more? Who thinks the direct effect? Raise your hands, let's have a poll. And who thinks the indirect effect, the effect of Serena hitting it that way less often, is going to win? And who's abstaining and basically refusing to be a coach? Okay, quite a number of you, all right? All right. Well, we're going to find out. We're going to find out. We're going to find out by resolving for the Nash equilibrium. What we're going to do is redo the calculation we did before, starting with Serena. So to find Serena's mix, to find Serena's new equilibrium mix, what do we have to do? Right? The question is, in equilibrium, is Serena going to lean to the left more, so Q is going to go up, or less, so Q is going to go down? So I need to find out what is Serena's new equilibrium mix. What's the new Q? How do I go about finding Serena's equilibrium Q? What's the trick here? Shout it out. 1, 2, 3. What's the... Use Venus's payoffs, all right? So to find the new Q for Serena, use Venus's payoffs. And let's do that. So from Venus's point of view, if she chooses left, then her payoffs are now, and again I should use the pointer, 30 with probability Q, this is the new Q, and 80 with probability 1 minus Q. 30 with probability Q plus 80 with probability 1 minus Q. Again, this is the new Q. I should really give it, I should call it Q prime or something, but I won't. And if she chooses right, then her payoff is what? It's going to be 90 with probability Q and 20 with probability 1 minus Q. 90 with probability Q and 20 with probability 1 minus Q. And what do we know about these two payoffs if Venus is mixing an equilibrium? And we know she's mixing an equilibrium because we saw there was no pure strategy equilibrium. So what do we know about these two payoffs since Venus is using both these strategies in equilibrium? They must be the same. Since she's using both these strategies must be equally good. They must both be best responses, so these two payoffs are equal. Since they're equal, all I have to do is solve out for Q, so let's do it. So I'm going to get 90 minus 30 is 60q is equal to 80 minus 20, which is 61 minus q. So q equals 0.5. All right, so don't, if I did the algebra too quickly, just trust me, I think I got it right. All right, from here on in, it was just algebra. All right, so what have I found out? Did q go up or down? Well, it used to be, q used to be what? 0.6, and now it's 0.5. So let me ask what I think is an easy question. Did it go up or down? It went down, right? It went down, right? Q went down. The equilibrium Q went down. All right, so which effects turned out to be bigger? The direct effect of playing more to your strength, or the indirect effect of taking into account that your opponent is going to play less often to your strength? Which effect turned out to be the bigger effect? The indirect effect, the strategic effect. Of course, I rigged it. I want the strategic effect to be bigger, because this is a course about strategy, right? All right? All right? But the strategic effect actually won here. The strategic effect, the indirect effect, is bigger. All right? And that's good news for me, because it says the slightly dumb coach who didn't bother to take game theory would have stopped at the direct effect, and they'd have told Serena to go the wrong way. But the smart coach who takes my class and therefore somehow contributes to my salary in an extraordinarily indirect way gets it right. All right? All right, the strategic effect is bigger. Now, we can also solve out for Venus's new mix. But and we'll do it in a second. But before I do it, let me just point out that we really can now intuit Venus's effect. Maybe not the exact numbers, but we can intuit it. So I claim that if we think this through carefully, we know whether Venus is shooting more to the left than she was before, or less to the left than she was before. Right? Notice that in the new equilibrium, Serena is going less often to her left, even though she's better at hitting the backhand. She's better at hitting the ball when she gets there. So since Serena is leaning left less often, what must be true about Venus in this new equilibrium? It must be the case that Venus is hitting the ball to the left less often. All right, that makes sense? That makes sense? We have enough information already on the board to tell us that. Nevertheless, let's do the math. Let's do the math. So, all right. Let's go and retrieve a board to do that. Just for completeness, let's figure out exactly what Venus does do. All right. So to figure out what Venus is going to do, what's our trick? I want to figure out how Venus is going to mix. I'm going to find out Venus's new P. How do I find out Venus's new equilibrium mix? I look at Serena's payoffs. All right? So if Serena chooses left, her payoff is, and I'll read it off quickly this time, is 70p plus 10 1 minus p. And if Serena chooses right, her payoff is 20p plus 80 1 minus p. And I'm just praying that the TAs are going to catch me if I make a mistake here. And I know these have to be equal, because I know that, in fact, Venus is mixing. I know that Serena is mixing. All right? So I know these must be equal. So since they're equal, I can solve out and hope that I've got this right. So I've got 50p equals 70 1 minus p. So p is equal to 7/12. So again, that's just algebra. I rushed it a bit. It's just algebra. Same idea, just algebra. So 7/12 is indeed smaller than what it used to be, because it used to be 7/10. All right, so that confirms our result. Okay. So the strategic effect dominated. Venus shot to Serena's backhand less often, and as a consequence, so much that Serena actually found it worthwhile going more to the right than she used to before. All right. Now let's just talk this through one more time. This was a comparative statics exercise. We looked at a game, we found an equilibrium, we changed something fundamental about the game, and we looked again to look at the new equilibrium. That's called comparative statics. And let's talk through the intuition. Before we made any changes, Venus was indifferent. Right? Before we made any changes, Venus was indifferent. She was indifferent between shooting to the left and shooting to the right. Then we improved Serena's ability to hit the volley to her left. It improved her backhand volley. If we had not changed the way Serena played, if we'd not changed the way Serena played, then what would Venus have done? So suppose, in fact, Serena's cue had not changed. If Serena's cue had not changed, remembering that Venus was indifferent before, how would Venus have changed her play? Somebody? So if we started from the old cue, and then we improved Serena's ability to play the backhand volley, and if cue didn't change, what would Venus have done? She'd never ever have shot to the left anymore. She'd only have shot to the right. She'd only have shot to the right, which can't possibly be an equilibrium. So something about Serena's play has to bring Venus back into equilibrium. It brings Venus back into being indifferent. And what was it? It was Serena moving to the left less often and moving to the right more often. All right, so again, if we didn't change Q, Venus would only go to the right, so we need to reduce Q, have Serena go to the right, to bring Venus back into equilibrium. Right, and conversely, if Venus hadn't changed her behavior, if Venus had gone on shooting exactly the same as she was, P and 1 minus P as before, then Serena would have only gone to the left. And that can't be an equilibrium, so it must be something about Venus's play brings Serena back into equilibrium. And what is it? It's that Venus starts shooting to the right more often. All right, so just two reminders. Before you leave, two reminders. Wait. First, in about 5 minutes' time, a handout will magically appear on the website that goes through these arguments again, all of them in 2 other games. So you can have a look at the handout. Second thing, a problem set has already appeared by magic on that website that gives you lots of examples like this to work on. All right, play tennis over the weekend for practice, and we'll see you on Monday.